I'd like to welcome you to the first EOL seminar of 2017. We're fortunate to have Simone Tilmes here to talk to us today. Simone is a scientist at NCAR and ACOM. She's been there for 12 years. For the past 6 years, she's held a joint appointment in CGD, and she has served as the community liaison for the Chemistry Climate Working Group of CSM. Simone got her PhD in geophysics, working at the research center in Jülich. And at that time, she was studying ozone loss in the Arctic polar stratosphere. Her scientific interests broadly include chemical, aerosol, and dynamical processes in global chemistry climate models. She has investigated the evolution of the ozone holes in both hemispheres, tropospheric chemistry and aerosols, air quality and long-range transport of pollutants, and as if all of that weren't enough, also the subject of her talk today, the impacts of geoengineering on the climate system. I just want to say how pleased I was that Simone agreed to give a seminar because this topic is important to me. It's important to all of us, really. It's moving out of the science realm and as well into public policy and politics. People are lining up on both sides of the issue. It's somewhat controversial, and it's something that could have serious consequences for all of us. So with that in mind, everyone please pay attention. There will be a test. Simone?
Okay, thank you, Mike, for introducing me and also inviting me. I've never given an EOL seminar before, so it's a pleasure. I'm talking about geoengineering or climate engineering, if you want. And first, I assume that people haven't heard a whole lot about it because I will introduce this method and in particular talk about solar radiation management. Is this okay with the speaker? Yeah. Which is also like something like aerosol geoengineering. I will go into the details. And then in the recent years, like about 10 years, there were more and more studies that looked at the effects of climate engineering, the benefits, side effects, and risks. And I will give a little overview on what was found and what are the problems or also the benefits. And then the last part of this talk is on new ways and to develop strategies to potentially reduce some of the side effects and some of the risks and make this option maybe a viable option if needed in the future. So as a motivation, of course, has to be given, why climate intervention research? And that's what I'm talking about, the research, not the application, of course. Everybody has probably seen this chart. This is global surface temperature warming, and this was in 2013. So we have these emission pathways in the future. And we see that we already have about 1 degree warming from pre-industrial conditions, and we're heading to quite a bit of more warming at the end of the century if we continue as emissions in a business as usual way. However, there are other scenarios that we may take. And right now we are right on the track. So what happens if we continue this? People know and heard about all the consequences, the heat waves, melting of the ice sheets in both hemispheres, flooding, coral bleaching, more forest fires, and so on. But then there was a breakthrough with the Paris Agreement. And actually in November last year, states have agreed that temperatures shall not go over about some certain limits. And the limits are about 1.5 or 2 degrees. That means we don't want to go about 1 degree warmer than we are already by now. The question, though, is can we actually achieve those goals? We are on track of emissions, and this is here illustrated in a nice study that just came out from Ben Sanderson last month in Nature Climate Science. And what is shown here is the global gas emissions, gigaton per CO2. We were heading towards more and more emissions. And now after the Paris Agreement, if everybody would start in this year, reducing emission in a constant rate, This is the pathway he calculated for the 2-degree goal, not the 1.5-degree goal. That means we'll have to start now, we have to go down. This black point actually shows the commitments that states have done for the Paris Agreement. So we may be able to reach it, maybe a little bit much. But then he also looked at a delayed emission period. What would happen if in the next 8 years, for example, for whatever reason, we would go the opposite direction and increase emissions again, and then go back. And we would not reach the 2 degrees, but maybe end up at 2.5 or 3 degrees. So the point of this study is really, if we go later, we may have to do way more. And so a little bit of delay, but that was meant for the whole world and not just for the US, for example, could change our reaching the likelihood to reach the target of 2 degrees or even less. And that is one example why even if we do as much emission cuts and as possible, we may not reach the goals to prevent worse climate impacts. Then that is the motivation to think about if there are other options, other methods. And what you already see here is people consider negative emission. And negative emission is also a form of geoengineering or climate intervention. And so I come to the next slide on explaining what is meant by climate engineering, or also called climate interventions. There are two main parts to it. One is carbon dioxide removal. That means we actually address the problem. We have increasing greenhouse gas emissions, we need to reduce them. And not just the emissions, but actually pulling them out and then actively store them so they don't stay in the system, because we know that CO2 has a very long lifetime. That will help us to get to negative emissions. There are different approaches. I mean, afforestation and biochar, there's a direct air capture, there's storage that is possible, but this is a whole different type of studies, and they are, so at the moment, these methods are very expensive. There may not be enough storage, as way more research has to go into these approaches. The other thing that seems to be in some way easier is what if we just block the sun? It will get cooler that way, and so we counteract the warming that we get from greenhouse gases. And people came up first with very expensive methods of saying, well, let's put space mirrors into space mirrors in the Lagrangian point and reduce the sunlight. Turns out to be very difficult, at least at the moment. Other ideas is to brighten the clouds. They reflect more sunlight. Or, for example, paint roof whites. They reflect more sunlight, so maybe we can do something there. And then the most prominent method, that I will talk about mostly, is putting reflective aerosols in the stratosphere. The reason why this is the most prominent method is that we actually have a natural analog for this. So volcanoes that are strong enough and the emissions reach into the tropics high enough into the stratosphere will form aerosols. And then they actually block sunlight and will cool the climate. And we do actually have temperature records that show that it seems to work. So there were some recent large volcanoes here in the last, 100 years. You always see that when a volcano erupted, there's some kind of temperature decrease happening. So we think that this method could be working. In particular, when you look, this is a nice movie from a study that has been done by Mike Mills last year. He used the WECAM model, and this WECAM model has the way you can inject aerosols, SO2, like the volcanoes, and then it forms the volcanic aerosol plume, and you can actually follow how this plume gets distributed over the planet with time. On the right, you see the time, and you can nicely see after that one eruption in June 1991, a large plume of aerosol is covering the Earth after a few months, and you also see that it goes up into high latitudes. So basically, for a long time, these aerosols stay in the stratosphere, they get transported around, they block sunlight globally. And after, of course, a few years, this effect disappears. So for geoengineering, the idea is to inject gases that will form aerosols and do kind of the same thing as the volcano. We can see that the temperatures are getting reduced, but there are also other impacts we have seen. So volcanoes, after eruption, they did cause the radiation to change. We see that here an anomaly from a probably some average of years. You see an increase in the reflected sunlight, and then in the net forcing, we see that we reduce here the radiative forcing right around the Mount Pinatubo eruption, and then it slowly went back to normal conditions. But what happens also is that the study by Trenberth and Died in 2007 saw that the continental discharge, the water runoff, we see a large drop, and this is also in agreement with land precipitation. So there seems to be some effects with this, and maybe there's a problem with geoengineering, and therefore it is really important to understand, before any of these approaches would be considered, what happens to the climate system. But of course we cannot just try it out, and we cannot just have a volcano erupt and measure what is going to happen. So of course we can use our Earth system models that we are designing. And so there was this initiative in 2011 called the Geoengineering Model Intercomparison Project that actually wanted to have several climate models to perform the same experiments to understand what are the impacts of geoengineering. And the first thing is to look at something more simple than injecting aerosols, just dimming the sun. I see also called it geoengineering and talking about climate engineering, whatever. So to actually look at the impacts not only on the global temperature, but also regional, on temperature, on precipitation, on the hydrological cycle, and on feedback processes. So we do need actually models that can describe all these different processes. Then, in addition, there are models, or if we actually want to look at aerosol geoengineering, meaning actually injecting gases in the stratosphere, we have to have more complex models. And within GeoMIP, there were only a few that actually could do those. So there are some studies that I want to talk in the following that have looked at processes and also side effects of these approaches. Just want to mention this GeoMIP intercomparison project for these experiments, pretty successful. There were about 40 papers that came out of that, and if people are interested, they can Google that. But I want to just summarize some of the results. And one of the easiest experiments that was actually getting us a lot of information and understanding of processes was this G1 experiment where 12 CMIP models have participated. And so these are simple models, and the idea is we're starting from a control simulation. That's 1850 control simulation. And then we perturb and have 4 times CO2 increase in that model. And so that, of course, will cause a warming. At the same time, and then there will be a second model run that has also the 4 times CO2 increase, but then the sun will be dimmed. So we will reach the same net forcing and see what happens. And so this is a really strong forcing experiment because 4 times CO2 is about equivalent to the end of the century climate forcing with a business as usual scenario. So, well, we may go there, but that's was really to understand what are the processes and what is happening. So, what we do see is in this, we call it 4 times CO2 control experiment. You see that temperatures are drastically increasing in the first 10 years, and then they're flattening out and slowly still increasing because the ocean is still acting and warming slowly. If we do our geoengineering experiment and dim the sun in addition, it's very interesting that most of the models actually got this, and we could get to no temperature change compared to the control. But what you also see is there's a bit of variability in the models. So some models warm a little more than others warm less, and that's called the climate sensitivity. So actually, all the models are a little different, and we are not really sure how much we would need to dim to get these temperatures, so everybody had to calculate and test out how much how much solar reduction they need. And that was quite a range on what you would need to actually achieve this. And then global temperature has been achieved. You could actually balance global temperature, but what about extreme temperatures? And what we found actually in these experiments was that looking at extreme minimum temperatures here shown, or just temperatures, you always would get an overcooling with this approach. It's a global solar dimming in the tropics and a warming in higher latitudes. And that kind of makes sense because you dim the sun, and the strongest effect is actually where the sun is shining. So you do have, of course, sometimes winter, you don't have any sunlight, and you would not get an equal effect everywhere. So this would cause a warming in these hemispheres. So what that means is, well, we get global temperatures can be reduced, but for example, the Arctic may still see some sea ice loss. We cannot quite recover that. We do see that ocean temperatures are getting quite a bit reduced, but there may be still a little bit sea level rise, but less. And definitely heat waves are reduced, but maybe not perfectly. And that shows already that, again, as we shown earlier, the method is not perfect. Looking at now temperature and precipitation in a different way, what you see here is the same experiments. This is now latitude and the difference in temperature for the 4 times CO2 minus the control and the geoengineering. But what we really see is that we do achieve quite a bit of cooling here, so the temperatures stay. You see that little bit of warming in this. What you also see is the land-ocean difference is a dramatic change for the 4 times CO2 experiment. What about the precipitation now? So what we see here is actually, even though in the geoengineering case we keep the temperatures fixed to the control, or we manage to balance those, precipitation is decreasing. And that's very similar to what the Drenberg et al. Study has shown. And we can also understand this. Well, if we, for example, look also at the evaporation changes here, we see that there is a strong change in evaporation over land. There are 2 factors that play a role. One thing is that if we dim the sun, we do not perfectly pull the temperature back as it was, but the stability, the atmosphere gradient of temperature is changing. And that can change how much evaporation we get over the ocean. The other thing is that plants react to the CO2. There's still high CO2 conditions. The stomata is actually closing a little bit when plants see that, and they don't evaporate so much. So the evapotranspiration is reduced. You also see that here in the 4 times CO2 case even. But then if you, in addition, geoengineer, you get a strong reduction here because you don't have that additional warming that would cause more evaporation. So from that, actually, we learned that you cannot, if you want to balance the temperature, you cannot really balance the precipitation, and the hydrological cycle will be slowed with this approach. There's another, And then if you go further, you can say, what is the impact on crops? So as I just said, what we can reduce is the extreme rainfall with this approach, and may get less flooding, but we may not prevent droughts, but though it depends. You can also argue that less evaporation of plants, they don't need that much rainfall, so the impact of the plants isn't really clear and has to look at much more. But there was one study by Shai et al. Looking at the impact of crops just from this experiment. And this is not a solar dimming experiment. This is an aerosol injection experiment, but it shows that there are benefits and there are also some disadvantages for crops. If you look at this increasing or climate warming scenario shown in red, in general reduces the yields of crops quite a bit. Only in one case, which is the temperate soybeans. And this is because they grow better in some places when you suddenly have some warming. However, if you add geoengineering to this, usually you get a little bit improvement in some areas because you simply cool the areas where crops have some temperature they like. So if you go out of the temperature, then they will not produce that much yields. If you then with geoengineering bring the temperature back, they may grow better. And there's also the fertilization effect of CO2 that we will still have. So just pointing out, there's many things that we still have to look at and understand. From simple experiments, you may get one answer, but having more complicated models, it may be different. There's one more risk that I want to point out with this approach. There was a study by Jim Haywood in 2013, and he looked at a moderate climate scenario. Here you see precipitation in millimeter per month, going from 1900 to 2100, and this is the period of solar dimming. The first chart has showed no solar dimming. So you see that precipitation in this case is increasing from the average value. When you do solar dimming, however, in one hemisphere, just in the southern hemisphere, you see a decrease in precipitation. If you do it in the northern hemisphere, you get an increase in precipitation. So that shows that the changes, if you have an uneven approach, or for some reason shortwave radiation is stronger reduced in one than the other hemisphere, you actually may risk to change precipitation patterns and to actually have some region that really experience more droughts than before, and that's the real danger of this approach as well. Another risk in one of these experiments, and this was also a GeoMIP experiment, the G2 experiment is also going from this 1850 control run. And people had simulated in 1% CO2 increase per year. You see this increase here in temperature. But you also see again all this climate there's a variability, but also that there's quite a bit of difference in climate sensitivity between the models. Then the models took what they learned from this 4 times CO2 experiment and scaled down how much dimming they need. And you see how well they did. There's quite a challenge to actually do this right in the models. Another risk is that what if we suddenly have to stop geoengineering? We have to terminate it. Well, we jump within 10 years right back to almost right back to the temperature where we were. So there's a huge risk that those things can happen, that you suddenly, some event, have to stop and get even much stronger and drastic change in temperatures than you wanted. So the next part, I want to talk about actually using aerosols to modify the Earth's albedo. And what challenges are there? Well, first of all, if you think about it, you will have to inject aerosols at an altitude in the tropics or close, maybe not quite 20, 25 kilometers. Bring it up there. And then you don't inject actually aerosols, you may, but you can also inject gases like SO2, like the volcanoes do. And then with time, these gases will form aerosols, maybe after 20, 30 days. They will coagulate, they will distribute over the whole planet toward the pole and then block the sunlight. But there's a lot of processes involved. The aerosol microphysics are important. We need to understand the dynamics in the model, the chemistry, because there's also impacts on ozone, for example. Aerosols are surfaces that increase heterogeneous reactions in the stratosphere. So climate models that we usually use also cannot really simulate the small injections that you might get from airplane and other ways. And so the question is also, what amount of aerosol do you need? There are more side effects to it, and the technology is also not developed yet. There's a big question on the cost and what are the side effects? How do we calculate them into the cost as well? I want to show a couple examples on what has been done on this. And earlier studies that actually had already an aerosol microphysical model was a study by Heckendorn in 2010. And really looking at what happens when we inject in the tropics with different amounts, and how does this change my aerosol distribution. And what you can see already here is there may not really be quite symmetric because of how the nature of the dynamics is in the stratosphere. And also, the more injection, you may not get much more change anymore because particles coagulate. And so the efficiency of a certain amount of injection is going down with the amount. And so that leads us to the questions, are there limitations on this? And for example, Jason here in the audience has done a study comparing different models and looking on the limitations. If you see, this is the aerosol burden that is achieved through a certain amount of injections. And so earlier models that didn't have microphysical models in them, for example, the first study was by Russia in 2006 already, you do see that the injection is much more efficient, but that's unrealistic. If you actually have an aerosol microphysical model in your model, you can see that particles, the efficiency goes down, and with injection, the burden is not growing as much as you would expect it from a linear function. So coagulation is a problem, smaller particles with large particles, and so it is important also to see what injection region would we use and what area, and people have looked at it, but all come to the conclusion there are certainly these limitations and efficiencies. So what additional challenges are there? If you can think about, you inject aerosols, or you form aerosols, you have an aerosol layer, you heat that layer because aerosols do have an irradiative impact. So you change the stratospheric dynamics and the chemistry. There will be an increase in stratospheric ozone. That is worse if you have aerosols closer to the tropopause than further up. That causes a delay in the ozone hole. There is impacts on air quality and surface ozone. And certainly one point is the implementation strategies and cost. So I want to just talk on these last 3 points now. One of the risks, as I said, is ozone, because we do inject right into the ozone layer. And the problem is that aerosols that are enhanced will form surfaces that increase the heterogeneous reactions, as I already said. They reduce the ozone column. And we do know that every year there is an ozone hole reoccurring over the Antarctic and also in parts over the Arctic. And with increasing aerosol, we make this problem worse. So we have calculated what the effect would be on the surface UV. And you can see that most impacts are certainly in high latitudes where those reactions are most important. You may even get an opposite effect in the tropics because there's also some ozone production in the tropics due to a different cycle, the NOx cycle, and I don't want to go into that. So there are opposing effects also from aerosols that are either leading to an increase or a decrease of stratospheric ozone. But in general, it only, of course, depends on at what time we would apply geoengineering, with how far are the CFCs already removed from the stratosphere. And at one point, these effects, of course, will be reduced. But this is an important concern that has to be looked at and to consider if this approach could be considered. I do want to show in about half an hour now. There's one other study that looks actually at surface ozone. It's just in preparation. And when you do look at a study where this is a scenario, which is the RCP 8.6, a climate scenario, we would inject a constant amount of 8 teragram of SO2 per year. You see that temperatures are increasing here, and with geoengineering we get that drop, but then they're continuously increasing because you have a constant amount of geoengineering. We do see that in the model that surface temperatures, I'm sorry, I wanted to point out that this is a contrast between two schemes. On the one hand, what we are doing here is we inject aerosols, and on the other hand, we are dimming the sun. And you can actually see that you get a very different impact on surface ozone. On the one hand, this is the climate change scenario. On the one hand, with solar dimming, you actually get an increase in ozone. On the other hand, get a decrease in ozone, in surface ozone. And this is caused by different effects. If you have aerosols, they deplete ozone and you get less exchange from high latitudes that in general also reduce ozone at the surface. Where on the other hand, if you just do a solar dimming approach, you actually increase ozone. And that's just an example how difficult it can be. I think it is time to maybe talk about things that are more applying to the EOL, to the seminar, and talk a little bit of ejection methods in the seminar. So how do we actually, and that's a large question, and how would we actually inject these gases into the stratosphere? And so there are ideas to use fighter airplanes and fill them with SO2 and then inject, but you have to get high enough, and that is probably not so easy. And there was in England a team that was proposing a SPICE field project. And they say we have a balloon here, and this is connected with a hose. And we would inject SO2 or aerosols in this layer while we are always refilling the gases through this hose. Now, that sounds a little bit difficult considering that you're in the tropics and 20 kilometers high to maintain that. So the idea was that they actually would try it out. And they wanted to really build this. They wanted to build just a 1 kilometer hose that was connected to a balloon. And then they wanted to just inject water to show if engineeringly this is possible. Can you actually do this? Well, what happened was that this experiment was canceled, and I guess they had problems with their patent, but much more problematic was the public outcry here, which shows that it's really not so easy to get those experiments ever even to test something like this. But there is another experiment that is actually proposed in here by Erythema. This is from the Harvard group. And that's called SCOPEX. It's a stratosphere controlled perturbation experiment. And in that experiment, they propose a stratospheric cruiser that would be launched in the stratosphere. It has propellers to move around, and it would be powered by solar panels. And it would also have a payload in it that could actually measure perturbations in the atmosphere. So idea is here, it would hang on a balloon, and this strat cruiser would maybe carry some kilogram of SO2 and water vapor. It would spray it out and perturb the atmosphere. And then afterwards, they would, with a LiDAR, measure where this plume goes, and then go down and actually measure what the perturbance in the atmosphere is to understand what is the chemistry, what are we doing. And I think they are still working on this and planning to do some kind of similar experiments in the future if they can, if they are allowed to do this. So I think for now I want to summarize what you have learned so far or heard from me. And what we have learned in recent years is that there are certainly benefits of geoengineering. So you can reduce global surface temperatures. Sea level rise may be reduced, heat waves, excessive flooding, and also you may reduce sea ice melting in higher latitudes. But there are side effects. And I haven't mentioned that at all. This scheme, of course, does not address at all the continued ocean acidification, because all you do is just address the symptoms. But we do have reduced sunlight that impacts the ecosystem and so on. We get a weakening of the water cycle, delay of the ozone layer, and also potential shifts in precipitation pattern and continued warming in polar regions. So there are a lot of uncertainties, especially the regional impacts, impact on agriculture, ecosystem, air quality, and implementation and costs. So also there are risks, like I mentioned, the sudden termination. And I think one of the main risks so far was that we really don't understand the climate system perfectly. Can we actually do this? And do we have any way to actually figure out how much injection would we need in a certain scenario, because we don't really know what pathway we are going. And so the next or the last part of the seminar, I want to talk about strategies that address exactly that question. And well, can you actually design strategies to address the unknowns of the system and also improve the climate outcomes? And that is a new way of thinking, of saying we're not just injecting something and seeing what happens, but actually turn it around and say, how can we change the strategy so we reduce the outcomes, the risks and the side effects? The other things we can do to reduce risk and side effects is to explore more reasonable scenarios where we actually consider pathways that haven't been, not these really strong emission pathways like 4 times CO2, but more realistic ones, and see what will happen. And other things are discussed, like can we maybe change the aerosols that are injected? Maybe there are others that wouldn't destroy ozone in the same way. So talking about the first point, I have been working with people here at NCAR, Diagarishta, Mike Mills, and then also by NCAR and Martin the last year on a study to actually look at strategies and say, can we develop an algorithm so we can meet certain climate goals, do geoengineering in that way, and also basically prevent from knowing what the climate sensitivity in the model is to annual decide on how much gases would have to be injected. And so to do this, we're looking at certain climate goals that we want to reach. The first thing is, this is a plot showing temperature change, as I've shown before, with global warming, you get a strong temperature increase. Now, if we dim the sun or do a global aerosol distribution, we have seen that we heat the high latitudes more than the low latitudes. So the idea is that not just having a climate goal of global temperature change, but also a climate goal of the equator to pole temperature gradient, to actually say, we design a system that we actually look at this gradient and try to remove it in our application. And the last is also the north to south hemisphere temperature gradient, which is illustrated here, because if you do dim or reduce the sunlight in one hemisphere more than the others, as we have seen, you may get changes in temperature pattern. And this has been actually shown already in models in just reducing the sunlight. So playing with the model is very easy. But what we wanted to show is this was actually possible doing it with SO2 injections. And so what we did is we used the MECHAM one here, which has new capabilities. We can now inject SO2 directly into the stratosphere, and we form interactively with gases, so we have an aerosol microphysical model and interaction with the dynamics and the chemistry. And we look at a scenario of an RCP 8.5 scenario, and we started running an experiment which we called the single injection matrix. So we wanted to identify what happens when we inject SO2 in certain points in the stratosphere, what is actually the outcome for the aerosol distribution, to basically identify what do we have to do to get a certain amount of dimming in certain areas and change the temperature that way. So we did all these experiments and decided that actually there are 4 points that we can actually control the aerosol optical depth, that means the dimming, in a way that we can actually achieve these patterns, as I have shown before, to get a quadratic or this function. And so what you can see and what you can learn is, for example, if we inject at the equator, we get a peak in AOD in the aerosol optical depth, and then we have less impact in high latitudes. If we actually inject in 30 north and 30 south separately, and what is shown here, the dotted line, is a high injection, that means 5 kilometers above the tropopause. The solid line is a 1 kilometer injection above the tropopause. You do see that most of the AOD is increased in that hemisphere where we inject, of course. We do see some bump here where we inject, and then a little bit more further on. And this is because of the transport. The Brewer-Dobson circulation actually produces this. If we're doing a 30 north and 30 south, we see that we can more control the high latitudes. And so we actually also did injections in 50 north and south, but that wouldn't add us really more control here because we would just get a little bit less of an effect because aerosols would be removed faster in this way. So then looking at temperature, you actually see that you do get quite a bit of an effect. But also it's noticeable, even though if the AOD looks pretty similar for the different hemisphere injections, there are different temperature patterns depending on where you inject, and you have to take that all into account. So the idea is now to take those injections and combine them together to get a certain distribution. But the question is, from our single matrix experience, can we actually do this? Because maybe if you inject at the same hemisphere here, if we add those up, we get a predicted distribution. But really, do we get this because particles coagulate and so on? So we did multiple injection tests to show how well we can actually combine injections to get the same result. And what you can see is it works pretty well if you inject in opposing hemispheres, but it doesn't so much quite if you inject in 50 north and 50 south. So there is some nonlinearity, and that's actually up to 20%. Even more visible here in the temperature, but it is manageable by feedback. And what does it mean? So we derive an algorithm that can actually tell us how much to inject to achieve a certain temperature goal. We have these 3 temperature goals. So what we do is we run a Wacom simulation and say we want to keep temperature as 2020 conditions. We run the next year and see it deviates from these temperature conditions. So we run our feedback algorithm. This has all the information that we got from this single experiments, and it will identify the location. But what we're not doing is say, okay, we have a half-degree difference. This is how much we want to correct to. We do it like a simulator, like aircraft simulator or something. You do not completely address the entire change, but do it over a certain period, like here 5 years, to get smooth changes, so you will not actually get really abrupt changes in temperature. And each time then, we decide on the new injection and run this. So if you think about such a scheme, you would be a lot of researchers to actually do this in reality, because what you wouldn't do is look at the past year to decide how much injection you need. You need to have data assimilation forecast possibilities. And certainly one important part is an observing system that we need to really understand where are we right now and how much do we deviate from the goal. And also the question is, what impacts does it have? We need to simulate, observe those changes. But this was just, again, a demonstration in a model. And what you can see here is that we actually reached those temperature goals. The first shown here, the global temperature. You can see that in the scenario that we chose was going from 2020, get this warming in this business as usual scenario. And then we did actually manage to keep the global temperature by every year adjusting the ejections. So we ran this feedback, which actually was first not clear if we ever even would manage that. Then we do have a look also not only at the global temperature, but at region the temperature changes, and also to see if we actually managed to cool high latitudes versus low latitudes. So what you see here is a movie where temperatures are changing with the RCP scenario. And now we started this feedback simulation at the right, and you can actually see how we managed to keep the global temperature. But then there are, of course, some regional changes and variability in this approach. This is demonstrating how much aerosol, or how the aerosol injection would look like. Of course, it wouldn't look orange like illustrated here. So really what we did achieve to keep these temperature goals, as I said, and this illustrates this idea that you can keep north and south temperature gradients and also equator to pole gradient constant. What is interesting also is this injection amount. We would have to go up to about 50 teragram of SO2 injection Well, what was, we were surprised that most injections were happening in 30 north and 30 south, so not at the equator, but more outside the equator to reach our temperature goals. And as a benefit, I mean, you do see that you actually can keep the Arctic sea ice from melting further. This is our CP 8.5 scenario. This was the feedback simulation. And we actually slightly recovered the summer Arctic sea ice with this run. And this is mostly because we got slightly cooler temperatures in northern latitudes in summer, which helped to reach that. Another thing is looking at precipitation. Did we manage to improve in the simulation? Well, compared to the RCP 8.5, we see much less temperature, precipitation changes. We do see some really strong changes, however. And looking at the global numbers here, in land precipitation, you see that decrease in precipitation like we have seen before. So that could not be changed with any of these feedback algorithms. And looking at aridity, actually we got an improvement. The land was less dry with geoengineering, but those results are very difficult to value because we just have one ensemble member. And it's really difficult to say something from just one experiment. So what we are planning to do now, actually starting this month, is to do a large experiment of geoengineering of this model simulation and want to address what are the regional changes and how robust are they, and really understand the processes. So I think, again, what we have shown here is it works, but it's not what we want to do. There are the risks that are still there. There's still the ozone loss, all what I have talked about. And for my last slide, I think there is one opportunity, though, to think about that this scheme could be applied in a way that is more reasonable. And thinking about having here the RCP 8.5 scenario, what if there is any pathway where will we go that we reach something like an overshoot temperature? Say we would actually start late, like I have shown in my earlier slide. We would start emission reductions too late, and temperature would still reach something like a 3-degree maximum. But then we could manage to bring them down. Maybe geoengineering would be a way to temporarily really cut off these high temperatures and stay under a certain target, so we would really reduce the worst impacts of climate change. But that would mean, of course, we would have to have some amount of injection. Doing the numbers for just 1 degree of overshoot, we would still have to inject like up to 18 teragrams of SO2, which would be a large challenge. And also you have to see that the timing would be like 160 years that this type of approach would have to be applied. But again, if it's a smaller amount, it may be a different story. So to summarize and maybe outlook, I want to just talk about maybe opportunities of aerosol climate engineering, since there were a lot of things you would think this is not a good idea. But we are still at the problem that temperatures are rising, and we may be able, actually, with geoengineering to prevent worse impacts of climate change and maybe tipping points that would not, that could be very easily reached. So there are side effects, but some can be reduced with the new strategies, and there may be new strategies and ideas that can even further reduce those side effects. So certainly there is much more further research required if people want to consider this. And so there would be new experiments that can be done with climate models that are more advanced than we have right now. Of course, the development of this strategy, this feedback strategy, can be much improved, because right now we just try to tackle 3 climate goals. Those could be increased regional climate goals. There's a large demand, if that would be ever considered, for technical development. How would that work? And what are the costs? Actually estimate those. And then, of course, we need a much improved observational network, which would be also very desirable after volcanic eruptions to have, because if we cannot right now really observe many chemical changes or aerosol effects, if a big eruption would occur right now. There is a large need for those in the future. And with that, I thank you for your attention.
Thank you, Simone. That's a lot to think about. We have time for questions.
Well,
Please, let's all use the microphone, please.
this 1 kilometer water vapor experiment that was nixed by the public, where was that?
In Britain,
I mean,
Great Britain.
Where?
In England, Great Britain.
Great Britain. And they were worried about just water vapor.
Well, because it was already associated with geoengineering.
Ah.
And that is the problem that people were worried about, that people would spray anything in. And so there was a lot of back and forth if this would happen, but they did not get it to be tested.
I mean, to me, that's a very small scale example of what is needed here, because you have to get international cooperation to do this, SO2 and, aerosols throughout the whole globe.
Well, yeah, especially if you, first of all, need an agreement internationally to do anything like that. And also you would need certainly different areas of the globe. If you would do it something like we have presented in injecting in the northern, southern hemisphere, it's not, if you just start at one place in the tropics, you may not even achieve what you wanted to achieve.
So you discussed the impact of global engineering on temperature, and especially the temperature distribution around the globe. One of the metrics would be looking at sea level rise. And that was particularly interesting out that, of course, in the poles and some scenarios it still keeps warming, which means you still get a sea level rise. Has anybody looked at that? What possible, basically sea level rise as a metric for possible impacts?
I think people haven't really looked at it too much, but we have looked at it slightly in these experiments that we have done, at least preliminarily. And so what we see is, since we're aiming for the global surface temperature, actually the 10-meter air temperature, we're not aiming to keep the imbalance constant. That means there is still heating going into the system. And that is exactly what's happening, is the ocean is still warming slightly. It's reduced, but it is still warming, so we do still get some sea level rise. So this approach may not prevent things like that have already started, like the melting of Antarctic ice sheets. And it does help, it seems, to prevent the summer sea ice over the Arctic, but it's a lot of questions that still have to be answered, and if it really addresses that. And to do it, actually, you keep sea level rise, you would have to do more than that. You would have to overcool your goal or your target, I think.
Right, it's not just the annual sea ice formation that's the issue, but really the melting of the ice caps, Greenland and Antarctica, of course.
That's the melting. Then you do potentially have change in dynamics that happen with geoengineering, with aerosol changing the dynamics. Then we change the jet streams. There are studies that show that it's actually warming. The peninsula would actually warm more because you, again, reduce or shift the jet stream in some way. So, yeah, it's a lot.
Fascinating talk, Simone. May I ask you to elaborate on this last in red, your point, much improved observational network. What it would take actually to monitor globally of what you need, and compare that to what is needed globally to monitor COP21 agreement, the Paris Agreement. And is there some synergy, some overlap with what would be needed? So COP21, one needs to monitor greenhouse gases, CO2 primarily. So what would you need there?
Well, besides all what you would need to the COP21, because that's the climate effects, you want to monitor what you're actually doing, you would have to monitor what happens, for example, in the stratosphere. So you inject gases, how do you change the chemistry? what happens, what are the effects, what are the reactions, and so on. I think that would be a really important part to monitor. And then, I don't know, I think that I could pose the question to you, because that's what you're doing. You could help me really figure out what would be needed to monitor.
Hi, Simone. So for continuous geoengineering, I assume we need to put lots of SO2 into the atmosphere continuously. So have you considered to generate those SO2? So SO2 is not anthropogenic waste. Now it's a kind of a product we need to generate for
That's right.
geoengineering purpose. How much energy, Earth's energy, how much Earth's resources we need to burn, we need to use for this geoengineering purpose, and how can it also have some negative impact on Earth's climate?
I'm not sure if I understand it right. Do you mean how much, for actually having the amount available, say 20 or 18 teragram of SO2, where do we get that from? I don't know. I assume that there is a lot of sulfate in coal or other places that you can mine and get out. I mean, there will be costs to it. We're trying to get the sulfur right now out of this. So at the moment, I think, and I'm not 100% sure at all, but I think it is about 100 teragram SO2 that we inject every year anthropogenically, which may include the volcanoes. But it is way more than what is right now thought to be ever used for stratospheric injections. But it's, of course, annually. But still, I think it seems to be manageable when you think about what we are already emitting right now.
Well, this SO2 will eventually end up as sulfuric acid.
Right.
Is that going to add appreciably to, say, acid rain, or does it add to acidification of the ocean?
I think it will add somewhat to acid rain, but again, the amount that we inject is much less than the amount that we have in the troposphere, though it will be a smaller fraction. As long as we're not going into these extremes that I have shown in our experiments to just demonstrate that this works. But I don't know if you...
There was a paper by Alan Roebuck about 10 years ago indicating that the effect on acid rain would be very small.
Yeah, Ben Kravitz was first on.
Okay, thanks.
Although those earlier studies always think about less injections than what is shown here, so or not that big of an amount, too. The more you inject, the more comes down, I think.
On the last point, and to pick up on what Wanda was asking, but to satisfy not so much the policymakers, but to satisfy your colleague scientists, what measurements are most critical to obtain in order to believe those parts of the climate models that affect this? How do we believe the climate models based on measurements? What's needed to demonstrate that we should be confident in them?
Well, I think besides climate, again, do you believe that what we inject right now will give us the forcing to give us a temperature change, say that way? Do we actually think that our models are correct enough that we understand how much injection we need?
We understand the forcing, but we don't understand the feedbacks.
Right. Right. So, I mean, in the end, we do have measurements of satellite that tell us something about the forcing, top of the atmosphere forcing.
For example, post-volcanic eruptions is so important to validate this.
Right.
They should justify and measure experimental.
And that's, yes.
See what's going on in the stratosphere after a large
Yes.
volcano.
And that is actually the case that some people come together already to propose that, to actually say what would we need, what measurements would we need. And after a volcanic eruption, we needed, for example, airplanes that could go and be ready to go with the required instruments to say, for example, what is the impact of different places in the atmosphere. We do need an observing system of the oceans and, of course, the surface temperatures as well to understand, and the hydrological cycle in some way.
In the absence of future observations that confirm this aspect of the model, I personally have very low confidence in the conclusion.
Well, that's why, actually, this feedback addresses this. The feedback algorithm says we don't understand the system perfectly. We don't know how much we have to inject. Will it be 10 or 15 teragram of sulfur in the end? But at least every year we will adjust the amount so we'll actually reach our goals. We may be quite a bit off in what we have estimated, what the injections are. And that may be also quite a bit of change in the estimation what the risks and impacts are, of course, which you couldn't foresee. But that's why one idea is, for example, for these feedback strategies, to run it in very many different models that have different climate systems, to understand if you can actually do this and manage it. So it's a way to say the system isn't perfect, but maybe there's a way due to those algorithms to still apply it, which is in a way an opportunity to not completely say this is not possible, I think. But that's a good question.
Are there any other questions? Yes.
Just a quick question about one of the last slides you showed talking about sort of temporary solar radiation management. In the late mitigation scenario that you had there, are you assuming any negative emissions?
Yes, we do, actually quite drastically, because in this case, we went to business as usual scenario and then did everything we could, including negative emissions that were from the literature possible. So this right away goes into reducing active emissions, but then also going into negative emissions by the end of the 21st century to reach actually this reduction in temperature, as you would not be able to reach that.
So the only way we can count on a temporary solar radiation management scenario, assuming these estimates are correct, is to also have significant negative emissions as part of the story.
If we start that late, then you have to count already on that, which isn't developed at the moment. That's true, at least from the study.
Thanks.
Okay, any other questions? All right, thank you again, Simone.